Marshall, you ready to go?
Yep.
You do your intro.
I think we're ready to start. Good evening, everyone. I'm Mary Portelli from the West Pittston Historical Society, and I welcome this wonderful large crowd out on this really cold Friday night, and we're happy to see all of you. We have a fantastic year of activities planned. If you're interested, keep your eye on our Facebook page, our website, and just Google us and you will find the West Pittston Historical Society. I also left some membership forms in the back. If anybody is interested in becoming a member, you can grab a membership form from the table in the back. I'm very happy to introduce our speaker tonight, Justin Emershaw. And Justin, most of you know Justin, I think. Justin is a mining engineer with the Atlantic Carbon Group, and I know he's going to put on a fantastic presentation for us. Justin.
All right. Well, thank you, everyone. I guess church is in session now, so here we go. I appreciate, first of all, everybody for coming out right before Valentine's Day to see this. And I do apologize and thank you again for coming out if you tried to come the first time and we had to cancel. So, so my name is Justin Emershaw. I'm the mine engineer with American Anthracite, located in Hazleton, Pennsylvania. Hold a Bachelor of Science in Mine Engineering, and I've been with the company for 10 years. And I guess a quick little backdrop about myself. You know, I never thought that I'd ever be working around here. My first job coming out of college was working in northern Minnesota. And then there's that old saying, if you've ever heard it, that once you get coal in your blood, it never goes away. It just drags you back in. That's kind of what happened with me. So in 2015, I started working for American Anthracite, and I got exposed to all the underground mining and the modern day mining activities, and it was just, it absolutely just lifted the history part of this heritage to me. So today's topic, and for those who remember some of my previous presentations, today's topic I chose slope shafts and plains. So, and the reason I chose this topic is because so many times when we hear on the news or in the media, we hear about mine subsidences, we hear about shafts, we hear about tunnels, and a lot of times nobody really explains what all this different terminology is. So this presentation is going to show you the engineering side of the entire mining industry. And as you're going to see, they didn't just go and dig around for coal. There was a whole method to everything they did. So starting off, let's talk a little bit about coal and where it came from, right? So we all know how it formed. It formed from swamps. But what a lot of people don't know is that there's at least anywhere between a 10 to 70 year time differential between the time when coal was discovered in Pennsylvania versus when it was actually developed, okay? There's an old saying. It goes, farmers found the coal, capitalists mined the coal. Because in these early days, in 1700s, even the early 1800s, everybody around here was farmers. They were merchants or blacksmiths. They didn't know anything about coal mining, but they, a lot of times, did discover some of the coal. Now, it's interesting because if you look back in history, you'll see there's lots of, I like to call almost legends of how coal was discovered. One of my favorite ones in the Hazleton region was how John Winters was out hunting and a deer just magically pawed up this piece of coal, and that's how coal was discovered. And we don't know if that's true because there wasn't, such a long time ago, there wasn't a lot of reporting on those subject matters back then. So it's almost become a little bit of legend almost on how or who first discovered it. But what we do know is when it was first developed. So once the coal was discovered by capitalists or business entrepreneurs, immediately these lands were either seized or purchased for acquisition, and then you have proving. So they know that the coal's on the ground, or it's been identified, but how do you know what's underneath you? In the early days, they would dig a lot of pits or sink a lot of small little shafts and basically do a lot of excavations and then try to locate the outcrop of these coal seams. And through this, they could identify how thick the coal bed was, and this is right where that coal seam comes to the surface, so they expose that. And then they could take a sample of it and determine what the chemistry was, the quality, even figure out the angle that that seam was laying at. And with this, then they could determine how that coal basin actually lied in the ground. For example, like if you look at this picture here at the bottom, if they took a proving of one outcrop of a coal seam here, and then another maybe several hundred yards in the other direction, they could make the assumption that it made a big U. Pretty much all of Pennsylvania anthracite lies in synclines, and we do have a lot of geological faulting of faults, folds, anticlines. So this was the early 1800s. This is how they identified the coal. Now, for mature mines, this is where we get into diamond drilling. And Rob here has a actual diamond drill bit from Corey.
Myself, I forget. But I'll pass it out. Just try not to drop it.
But so what diamond drilling is, and there's two ways that it's done. Sometimes it's done from the surface. It demonstrated in this picture right here. You can see where they came through the ground and they located the different coal seams. And other times, when a mine is more mature, diamond drilling, I like to say, acts as the mine's eyes. So even though they were developing underground drive-in tunnels, gangways, they had to have some clue of what was in front of them. And if you look at this picture here, that's what this identifies. So here's a tunnel underground, and at a point in this tunnel, they decided to drive these long diamond drill holes, which basically pull out a giant core. It's basically coring. And when they intersect a coal seam, they could then model that and determine where that coal seam is in front of them, what angle it's laying at, how thick it is, and that's how they determined where to advance and drive the entire underground mine. And then from a lot of the core samples, they could develop these stratigraphic columns. So if you look at this one here, it labels every different type of rock strata, and you can see in black is where they hit the coal. So this allowed them to basically understand what they had and how they wanted to attack developing it. From this, cross sections were developed. So geologic sections are traced, they're based on diamond drilling, and they're also updated as the mine advances. So once they knew what they had underground, this is when you see the collieries begin to form. So you'll begin to see a lot of the different land parcels start to get purchased by many entrepreneurs, capitalists, many from New York City, Philadelphia. There was a lot of interest that would come up this way to acquire all the different lands. And many of these properties were purchased for pennies on the dollar. And it doesn't really show up well, but for example, this map here, this is drawn in 1873. So this is just a mapping of the Lycans Valley Coal Company's properties down in Schuylkill County. So once the lands are acquired, then it's time to build the towns and the structures. And if I were to ask you, what did the coal companies own around here? What's the answer? That's a good answer, because that's exactly what they own. And this is a map of the Wyoming Valley, and from Mackinac all the way north, these are outlines of all the different colliery boundaries. We are actually in Pittston, which is right here. So as you can see, in the northern field basin, there wasn't one speck of property that didn't have coal on it, big coal, that wasn't controlled by big coal conglomerates. So now that the properties have been acquired, the mining rights obtained, now we get into mining. So now we're going to talk a little bit about just how exactly they mined all this coal underground. Drifts, if you've ever heard the term drift is one of the oldest methods of extracting anthracite. And with a drift, basically where the coal seam outcrops right near the surface, they would punch straight into it and drive gangways just like you see here. So this is a picture of a drift. This is actually the coal seam, and you can see the tracks going inside of it. That coal seam came right to the surface, and then they drove in. This map right here displays some what drifts look like displayed on an underground mine map. They usually have a little Y symbol at the end of them to show where the mouth of it is. And as you can see, they just go horizontally straight into the coal bed. The earliest drifts were primarily mule and wagon haulage. And later, if the drifts weren't exhausted by then, they would upgrade to electric haulage and things like that. Another early method of mining anthracite is called a water level tunnel, which later on, many of which would become drainage tunnels. But in this situation, say you have a mountain like down here that's traced. What they would often do is come from the very toe of that mountain and drive horizontally straight in. And this allowed them, the reason it's called water level tunnel is because if it's at the base of the mountain, all the water could come down the coal seams, hit the tunnel, and drain naturally out. That's where the term comes from. But you can see all the different coal beds that this tunnel is hit. So this is very early method of mining, and they would feast on all of this coal above the water level until it became exhausted and then begin developing below them. Here's a picture right here, an old water level tunnel, kind of giving you an idea of what one looks like. And here's another map showing one down in Schuylkill County. So once it started to get that they needed to get deeper underground, now you get into slopes. How many have heard of slopes before? Anybody familiar with the slope term around here? Okay. These were primarily driven where you get substantially deep coal basins. Because once all that coal that's above water level, it's easy to access, is gone, they had to venture further deeper. Slopes are essentially inclined planes that can extend hundreds, thousands of feet under the ground, but they are normally within the coal vein. This is an example of how big some of these slopes are. This particular one is Shendo City Colliery down in Shendo. The one downside with slopes, and you'll see later on why they were replaced by another higher productive method of mining, max capacity on average was about 250 cars a day. So it's times 3 tons per car, 2 tons per car, and that's how much on average a large colliery slope could produce. Another kind of slope that you may never have heard of before is called tender slope. So you got this big slope that's where all the coal cars are getting pulled up and down constantly, round the clock. But you need to have a way for men, materials, and machinery to get into the mine. Kind of like having a secondary escape way or something. So this is they would also think what was called a tender slope. And if you look on this mine map here, this is the main hoisting slope going straight down into the coal beds. And directly next to it, this is the tender slope. It's in the same coal vein. The only difference is one is being used to hoist coal cars consistently and lower them up and down the mine. And another one is how the workers actually got into the mine. Look at these guys going to work right here. This is how they would actually get lowered into the mine. This picture here is of a tender slope at Susquehanna Coal, and you could see how the tracks just start to dive off. This is called the man trip. So all the guys would get in here and sit. They had seats almost like these church pews stacked inside, and you could see all the guys sitting there, and then they would get lowered down into the mouth of the slope, which is demonstrated right here. So once you're underground, this is where they begin on a slope developing lifts, sometimes also called levels. Just depends on the colliery and how they chose to use terminology. Lifts and levels is basically the same thing. So if you take a cross section of this slope right here, here's a little engine house at the surface, which inside would be a big steam engine or with a hoist drum that would basically be attached to a long cable, and it would pull the coal cars up and lower them down. if you took a flat view, a plain view, if we laid that coal seam out, when this slope, this is that same slope coming straight down, at every 150 to 200 foot vertical elevation change would be considered a level. And this is where they would turn and begin driving the gangways. And this is where you would, if you were to, back in the 1800s, if you were to be a visitor at a coal mine and you said to the superintendent, I really want to go to the face. The face is here. It's where the guys are physically blasting, loading, and shooting all the coal. And they would continue to drive these gangways horizontally, perpendicular to the slope for hundreds, if not thousands of feet, and just keep following the coal seam. And the way they mine this, a coal gangway, the workers are inside the coal seam. So for example, if you look at this picture right here, this is the Mammoth coal seam, which is, how many are familiar with the Mammoth seam? Or up in northern field here, sometimes it's called the Big Bed, right? But basically it's Mammoth, it got its name Mammoth because it was just so big, 20, 30 foot thickness. So down here in this lower corner, this is the coal gangway. So this is where your mules would be. This is where the coal cars would be. This is where the men would be. And this is a cross section looking through the strata. And then here you can see where a chute has been driven. And this area up here, this is what's called the breast, which is also drawn here. And this is where they would pack that coal full of explosives and just fire it. And then once that coal is blasted, it would come down these chutes and it would get loaded into the awaiting coal cars. Basically, the car would be below and the chute would be above, and it would just drop that coal right inside. Here's some pictures of what some coal gangways look like. So they're always heavily timbered. Because when you're in coal, chances are it's definitely not as stable as rock. A lot of times it has a tendency to run. So you'll see the props are positioned about every 6 foot, sometimes even closer, depending on how unstable the top is. And then you have the top timber, which is called the collar, and the props or the legs, which are on the sides. And this whole basically this cage of timbers is to protect the miners from roof falls or coal falls. Here's one down here. You can see this train of coal cars. This is the Mammoth coal seam in Latimer, Pennsylvania. And what's cool about this is a worker right here. This is all coal. It just gives you the scale just how massive it was working in these giant chambers. Now, once you get into probably the turn of the century, 1900s, 1920, you're going to start to see a lot of coal gangways not being driven as much, especially where the coal is super thick. And in turn, what you see is rock gangways. So what's the difference? Well, rock gangway is driven in rock, and there's a reason for that. Once the coal was first mined within these big coal seams, they would come back later in the 1900s, all the way up until the 60s sometimes, and they would drive what are called a rock gangway, which is essentially a rock tunnel that is behind or beneath the coal seam, and it follows what that seam does from a distance back. So for example, here, this is a coal seam right here. This is the Mammoth again. And if you see these little things right here, these are rock gangways. So the men are nowhere near that coal. They're way back in solid rock tunnels like this. And here's a drawing to show just how these tunnels were designed. So for a double track tunnel, this one here is designed at 21 foot wide by probably 8 foot tall. Single lane car tunnel might be 7 foot by 7 foot wide. And inside this rock gangway, they would drive what are called rock holes, which are all these little things that you see here, okay? And on this picture over here, this is a really complex one. This one's really cool. Here's the rock gangway right here. And if you see this dotted line, this is the Mammoth, and it's doing a really funky, weird formation around this anticline where it's actually going up like a spike. And sometimes if you look, you could see little coal gangways that are drawn in that cross section. And that's where the miners were in the 1800s. But now to try and recover all that coal, because they could never support, with roof support, they could never extract 20, 30, 40 foot of coal without having to leave a lot. Rock gangways allow them to really mine and take almost everything. How they did that was, if they were back here in this haulage gangway, they would drive this rock coal up and hit the coal seam. And sometimes they would do what's called a rock chute, which is what this diagonal rock tunnel is right here. And from there, they would drive a long hole drill pattern. And this is basically a ton of drill steels that spray out in a butterfly fashion like this. And what they do is they fire all that coal. Now, it doesn't matter what happens inside the coal seam, because the miners are 50, 70, maybe 100 foot back inside of this rock tunnel. Nothing's coming down on them. And all that coal would be funneled down these chutes into the rock gangways where all the coal cars are sitting. So the rock gangway method enhanced not only safety, especially when they were robbing the mine out, but also permitted maximum coal recovery. Another term that you might have maybe heard of is a plane. Planes are also sometimes called inside slopes, depending on the terminology that the colliery likes to use. And this is an example of an inside slope, a hoist drum right here that's deep underground. And if you look at this map right here, what these were for was to pull the coal cars from one working level to another. A lot of times, instead of investing the money to drive major development levels, they would work the coal seam at different levels, but only pull the coal cars out on the top level. So say right here, this is 3 levels of development. Here's a haulage way down here, here's one here, and here's one here. So let's say this is 4 levels. You can see right here where it says plane 3, then here it says plane 2, and here it says plane 1. So if you think about what they're doing, they're taking all this coal that's laying on a steep incline, and they have an engine sitting down there, a hoist, and they're pulling all these coal cars up to this level. And then they're getting pushed down here, and they're getting pulled by another hoist up to this level. And then they go over here and get pulled up this level. Most likely because this was either a tunnel entrance or maybe a slope came down here, and it just saved them the money from having to do a major development to sink either a bigger slope or a shaft or something like that to really get deeper inside the mine. So now comes my favorite part. How many are familiar with shafts? Yeah, a lot of people are. Okay, cool. These are the workhorses of mines. And you probably a lot of times hear the term, oh, a shaft opened up over here or that. These things, when they do open up, are scary. So how many are familiar with what happened in Glen Line a couple of years ago? Anybody followed the news where the mine shaft opened up and almost the whole one building almost got sucked down? There's a reason for that. These things are hundreds, if not thousands of feet deep, some measure, and they're measured by the size of their compartment. So here's a guy standing in an underground shaft. They're essentially giant elevators. So here you can see the miners standing next to the coal car, and that goes straight down maybe 800, 1,000 feet. And it goes to different levels. It's just like an elevator if you were to get in a skyscraper. It's no different. It's the same thing underground. This is a really cool picture looking straight down one from the top of the head frame. How these things are sunk is very cool to get into the science and engineering behind it. This is a shaft right here that's down at Lehigh Coal and Navigation. And every one of these horizontal lines that you see, that's a level. That's a different level where all the miners would be working. So this right here, they're calling second level. Here's third, fourth. This is fifth down here. And if you look, they were proposing driving a 6th level and a 7th level, which are penciled in right here. How did they do that? There was 2 methods on how they would extend a shaft. And it's pretty cool how they could do it. The first method is a sink method, which is displayed over here in this little picture. Basically, if the shaft came down and ended, say, at this 4th level landing, they could drive a rock hole from here and drive straight down and then survey to the center line of where that shaft comes down and then start to sink in rock straight down. The downside with this method is just the amount of labor that's involved in hoisting of material. The more economical method that I personally think was pretty wild how they would do is a raise method. So say this shaft was down here at 5th level, and now they wanted to develop a 6th. What a lot of collieries would do was sink an inside slope or a plane and get the miners down to that 6th level where they wanted that shaft to come to. And then they drive a tunnel and come directly underneath where that shaft is to 300 feet above them. And they would drive straight up. And the benefit, if you think about it, all that rock could then get funneled through chutes right down into coal cars. The benefit to both these methods, primarily really with the raise, is that it doesn't interfere with coal shaft hoisting. They never would want to shut down a shaft back in the day when they were extracting coal. These were the money makers for the mines. And they could extract over 1,000 coal cars a day, roughly at about 47 seconds of hoist time at about 1,000-foot elevation change. So you think about it, that coal car goes down at 20 some seconds and comes up at 20 seconds. They were extremely quick on how they extracted the coal. Here's a engineering plan view down bottom here. And this one shows, this is the shaft here that they're proposing, maybe on this 6th level. And they're showing where they want the empty car lines to come in and where they want the loaded coal car lines to come in. And there was a lot of engineering calculations that went into this as far as how big to make the tunnels, where to stage cars, and just how much tunnel area needed to be open in order to make this thing literally not stop hoisting coal at any time. So, let's talk a little bit about timbering. I'm sure everybody has heard of props and timbers, right? We all know that they use timbers. What do they use them for? Well, the primary method of a timber is actually to alert the miner in case of a potential or coming roof fall. Because if you look at how they're mining this seam of coal right here, and here's the coal car and they'd be loading it, and they have all these props staged here. If this roof started to break, in many times, the timber would start to splinter and crack. And this is where you'd often hear a lot of the old stories of the mules being the miner's best friend. I've read countless stories and testimonies of how the mules could detect the sound of squeezes, which is when the coal just starts to squeeze because they took too much or the timber's breaking. The mules could actually alert the miners of a potential danger. Here's a diagram of how they would timber a shaft. So shafts are framed with a ton of different large beams, sometimes steel, and they basically make this giant cage in the cutout that they have underground. And here's a coal gangway or maybe a drift, and it shows the 2 double lines of track, the collar and props, and you can see all these battery or planks that are laying over the top of the collars. That's just to prevent any coal or debris from coming down on these miners. It's basically making a tunnel for them to travel through. Ventilation. So, back in the day, it's amazing to think, but back in the early 1800s, a lot of the times, mines before there were safety inspectors and there was rules and regs, were allowed to use what was called natural ventilation. And this is basically, there was no air coming into the mine other than whatever the opening provided. And this is where you would find a lot of the door boys. Does anybody know what other name he would go by in the mine?
Nipper.
A nipper, yes. So these young lads were employed to open and close the air doors. And the specific purpose of an air door is to regulate that airflow. They didn't want the air to go into workings where they had already exhausted the coal and everything was collapsed and mined up. It's just wasting air. So they would often close that off to control that ventilation so it only went to where the miners were actively working at the face. Later 1800s into the 1900s, you saw the installation of a lot of big mine fans. This is a drawing of a fan house and one shown right here. So there's everything from the turbine fans to like the ones that were just recently saved and taken down to the number 9 coal mine, which are some of the oldest wooden paddle fans. And these would force air. There was 2 types actually. There was either a blow or a pull fan, and they would either force air into the mine or exhaust and pull the air out of the mine. The mine's lifeline was always the pump house. And these structures were pretty wild to comprehend actually how they did this. So early pump houses were often installed in coal and sometimes were timber lined. Later ones that you'll see, like this pump house shown right here down in Tamaqua, is solid steel reinforced construction. It's inside of rock. And if you look, you can see all the steel I-beams, and there's the banks of pumps. And this is what would constantly be running to dewater the mine. Now, how many have heard of how, the NOx, we all heard about the NOx, right? Broke in, flood the mines, and then that was it. You want to know why that was it? Take a guess how much, and I'm going to give you an example based on our current electric bill where I work, because we are running 3,500 GPM vertical turbines to actually lower the water at our one surface mine, and we're doing that so we can continue to extract the coal. Guess how much the electric bill is to run 2 of those pumps 24/7 around the clock? $88,000. Now put that back into the turn of the century, 1950s, and they didn't just run these for a month or 2. They had to run non-stop to keep the mine dry. And here's a nice engineering design of a pump room and how it was instructed. So here's the foundations. Here's the column lines, which would go and actually pull the water from the sump. And here's the discharge lines in blue, which would take that water out of the mine. So, who came up with all this, right? There's a ton of things that went into mining that we talked about. How did they design this? This is where you had the engineer corps. And the collieries back then had 10, 15 or more engineers / surveyors working underground at all times. Look at these lads right here. Young guys, probably 18, maybe 20. These guys are down at were working down in Cranberry, which is right outside of Hazleton. This picture right here shows a miner actually using the scope to take a survey looking up the coal pitch. And the engineers, the surveyors, would map out the entire mine. They would survey everything from every tunnel, every coal breast, everything that the miners did, every angle, every change that coal made. They surveyed it. They bring that data to the engineers. The engineers designed the mine. And what they gave us was the vein maps. So some of you might be familiar with some of these. And they're very colorful, as you can see. Every one of these little red and yellow and green shapes is a coal pillar. And they're not just traced on there, just assumed. Every one of them, if you look closely, has a different shape. Every one was physically surveyed. And then that data was transferred to the engineers, and they would update the mine maps. All the different coal veins are always drawn in a different color. So, for example, here, Mammoth is drawn in red. This would be probably the Skidmore back here in black. This is the Buck in green. And these workings maps are basically looking straight down on the coal seam. So it's a two-dimensional view. If you took that coal seam that's lying in a syncline and you laid it out flat, this is what it would look like. Now, you'll notice here you could see all these little hatching areas. What do you think that means? Robbing. So anytime you see the hatch marks on these coal pillars, it wasn't just drawn on there for the sake. They physically were given authorization by the coal company to begin to retreat mine or rob out that section of the mine. We all know where the coal went after it left the mine. It probably went to, I would say, one of the biggest icons that we have that represents our history, and that's the breakers, right? Everybody's familiar. We recognize what these look like. We see them in pictures and photographs. And every colliery, it's pretty cool. I don't think I've ever seen one coal breaker that's looked the same. They're almost all different. And their mechanisms changed over time. Does anybody know where the word breaker came from? So, in 1843, there was a gentleman whose name escapes my mind at the moment. John Batten, I think his name was. I think he was down by Tamaqua or somewhere down there. He invented a machine before these plants were ever built. He developed a machine that was called a coal breaking machine. And it was basically two jaws that were steel with spikes on them. This is back when they used mule haulage and everything. And they basically would dump the coal inside of this little device, and it would go like this and crack the coal. It was called a coal breaking machine. And then later, because anthracite is so hard, unlike soft coal, because you've always had to break it, and it doesn't just fall apart, that name just stuck, and that's how in soft coal they would call these preparation plants, in anthracite we call them breakers because they physically broke the coal. When these plants were built, they employed a similar device as a coal breaking machine. They used rolls, which were giant steel drums with spikes, which would spin at high RPMs, and the spikes would roll together. The coal would drop in where those spikes are turning and just splinter and break apart. And later, as time went on, there was all different types of, you could do a whole presentation on all the different types of coal processing equipment that changed over time, from cyclones to heavy media to jigs. There was all kinds of different equipment that they used to wash, clean, and size it. And these collieries were substantially large. I felt obligated to employ a picture here of 44 breaker, which is right here. So some of you have never seen 44 breaker. That's what it looks like right there. So I couldn't think of a better way to end this presentation than pretty much the men, showing off the men who made our heritage, right? And, you know, what I decided to do for this slide, which didn't take too long because when you go through pictures, you will actually find these guys actually, in many cases, really loved what they did. And it's not very hard to go through photo albums and see a lot of smiles. These were proud men. In every Anthracite History Month, a lot of times we get stuck on the negative and how there was hardships and labor issues and the breaker boys. But what's often forgotten is the fact that back in this time, especially 1800s, didn't matter what you did. Didn't matter what industry you worked in. There was no safety. There were no regulations. Child labor existed in all different industries besides mining. So a lot of that's kind of given the mining a really bad rap in that sense, but these were very proud men. And at the end of the day, and I'm sure some of my UGM friends that are in the audience here will agree, you get satisfaction. Men get a lot of satisfaction with accomplishing something at the end of the day. And that's what these guys really felt. So that's the presentation. I hope everyone's enjoyed it. And before I do forget, because I know I did, if anybody is interested, the Underground Miners, UGM, are sponsoring another Movies in the Mines event at the Niagara Park in Scranton. So if anybody's interested in seeing that, it was a really awesome turnout, first time. Chris here could highlight some more information about that. But thank you so much for your time. Appreciate it. Yeah, so I'll open the floor to Q&A. It's always a good time for some Q&As. Go right ahead.
Those dewatering pumps, how high could they lift?
It depends. I've seen some plants that could go about 400-foot vertical lift. Normally, they usually try to get the pumps to discharge at an older water level or drainage tunnel, which in many situations reduce the amount of head by 150 to 300 vertical feet. Any other questions? There's got to be some. Go right ahead. Hi, Billy, go ahead.
Maybe explain to them, like, in the times before electricity, when they just had steam-powered shaft, how they pump the water out with those cisterns and dump them.
Yeah, so, and I cut a lot of this down because I didn't want to go too far over. There were so many pictures I could have thrown together here, but the older steam pumps, they'd all have a suction line that would go to what was called a sump, which is a sump to just collect the water. And they worked off steam power, so it was essentially everything back then was steam engine driven. So the piston would basically, when it drew, it would develop suction, which would pull the water into vessels, and then when it would extend, it would force that water up and out the column line. Those kind of pumps usually kind of, if you've ever seen one working, they kind of give off the blurp, blurp, blurp kind of flow of water. Whereas a modern electric pump, which began replacing the steam pumps in probably the 20s, 30s, they could just go full bore, high RPM, and they could double to quadruple the output of an old steam pump. Go ahead.
So if I'm not mistaken, what you're saying with the pumps, they would be positive displacement piston pumps, right?
They were all piston pumps. You had some that were cross compounds, some were triple expansion style. Most of them were horizontal engines. So they would be a high and low pressure cylinder. And I mean, to give you an idea how big these things are, the pictures, even for scale, don't do some of this justice. Some of these pumping plants that were underground and still exist, they're still down there, just full of water and debris. I've seen ones before that were 50 foot long by 35 foot high. That's probably almost as big as this room. And that would house this massive steam engine. It's amazing when you see just how large this machinery was and how they got it down there. It's really impressive.
So would they prefer electric power for it or compressed air in the later stages?
It was steam power initially, and then they later would upgrade and switch a lot of those older pumps. They would swap them out for electric. One of the big pumps that became popular in probably the 40s was the automatic centrifugals, which those were designed where you could eliminate having the use of a pump attendant. So they were designed to run, and they'd have a meter that would be monitoring the gauge at the sump, and when that water would get too low, the pump would automatically shut off, and when it would rise, it would turn on again. Those were called electric automatics. Those were popular. The other thing too to mention, many of these pump rooms were in watertight chambers. They were designed with big steel doors to hold back water, and the idea was if the mine ever flooded, if they knew the flood was coming, they could shut those doors, and that would prevent that water from getting to the pumps, and then they could continue to run and draw everything down.
Now, I've read in some older reports on, underground mining drilling that I believe that off the discharge line of some of these pumps, these continuously running ones, there would have been nipples and valves for using that as a water supply for drilling. Do you know of any documentation, anything similar?
That probably,
Never read one.
I wouldn't doubt that existed. It definitely, I know it existed underground. So, in many times, you know, when they would go to drain mines and advance in areas, it wasn't uncommon for these guys to be down 500 feet underground, and then say that colliery acquires another colliery that's adjacent to them, that's been abandoned for 30 or 40 years and is flooded right to the top. These guys would engineer to actually go and tap that water by drilling horizontal holes and bleed that water that could be several hundred feet above them
So that
and
way-
drain it down to the